Hi, hello everyone. This is Dnyaneshwar Sanap working as an assistant professor in the Department of Chemistry at Maratha Vidyaprasaraka Samaj, Arts, Commerce and Science College. In this video lecture, we will discuss about the different geometries, that is stereochemistry of an coordination compound with the coordination number 1 to 12. Also, we discuss about the factor affecting to the stability of metal complexes. And last point is the difference between the metal complex and the metal chelate. Let us see one by one. The first one is different geometry, that is stereochemistry of a coordination compound with the coordination number 1 to 12. Let us see one by one. Basically, most of metal having the coordination number range from the 1 to 12, but the most common coordination number is 4 and 6 out of 1 to 12. Let us see the one by one coordination number and their geometries. The first one is coordination number 1. And the example for the coordination number 1 compound or complex compound is Na plus Cl minus In pair in the vapor state. Next, the geometry, that is stereochemistry for an coordination number 2. Basically, coordination number 2 has two geometry. The first one is linear geometry and second one is bent geometry. Let us see the example one by one. Example for the linear geometry is AuCl twice minus and HgCl twice minus. The example for an bent geometry is unknown till. The next coordination number is 3. There is two geometries for the coordination number 3. The first one is trigonal planar and second one is pyramidal. Let us see the example. Example for the trigonal planar is HgI3 minus and the example for pyramidal is S3O plus In. The next coordination number is coordination number 4. Basically, coordination number 4 having two types of geometry. The first type of geometry is an tetrahedral geometry and second type of geometry is an square planar geometry. The example for tetrahedral and square planar geometry is like this. Example for tetrahedral geometry is CuCl4 2 minus and the example for square planar geometry is CuNS3 2 plus. Here the metal is same but the ligand is different. This chlorine ligand is an weak field ligand, that's why it gives an tetrahedral geometry complex, but the ammonium ligand is a strong field ligand, that's why it gives an square planar complexes. Let us see the structural representation of an both geometry. For tetrahedral geometry, the metal atom is at center and all these 4 atoms or 4 ligands or molecules at the 4 corners with respect to the metal atom. Here the angle between two ligands or two groups is 109 degree, here 109 degree, here 109 degree and 109 degree. And that's why this geometry is an tetrahedral geometry. Similarly, for the square planar complexes, the metal atom is at central point and 4 ligands at the 4 corner, but the bond angle between the two ligands is 90 degree, 90 degree, 90 degree and 90 degree. All these 4 ligands are in the one plane for an square planar complexes, but for tetrahedral complexes these 4 ligands is around the metal atom in the 360 degree. This is the major difference between the tetrahedral and square planar complexes. The next coordination number is coordination number 5. Basically, coordination number 5 has two types of geometry. First one is trigonal bipyramidal geometry, that is TBP, and second one is square pyramidal geometry, that is SP. The example for both type of geometry is FeCO5, MnCO5 minus, CuCl5 3 minus for an trigonal bipyramidal geometry. Similarly, the example for square pyramidal is the basic structure or stereochemistry for an coordination number 5 to the trigonal bipyramidal as well as square pyramidal is like this. In case of trigonal bipyramidal geometry, the metal atom is present at the center and the 5 ligand attached to the center atom is like this. Here 3 ligands with the dihedral angle 120, 120 and 120. These 3 ligands, that is ligand 2, ligand 3 and ligand 4 are within one plane and ligand 1 and ligand 5 are out of the plane. One of them, that is ligand 1, is above the plane and one is below the plane. This is the basic structure for a trigonal bipyramidal geometry. Let us see the basic structure for a square pyramidal geometry. Here, metal atom present at the center and 4 ligand, that is ligand 2, ligand 3, ligand 4 and ligand 5 are present at the 4 corners with the dihedral angle 90 degree, 90 degree, 90 degree, 90 degree with respect to each others, and the one ligand which is above the plane or below the plane with perpendicular to the ligand 2, 3, 4 and 5. This is the basic structure for a square pyramidal geometry. Out of these two, this trigonal bipyramidal geometry is most common geometry rather than the square pyramidal geometry. The next coordination number is coordination number 6. Basically, coordination number 6 having two geometries. The first one is octahedral geometry and second one is distorted octahedral geometry. The example for octahedral geometry is ML6, that is metal with the 6 identical ligand, and the example for distorted octahedral geometry is ML4L2. That means there is two set of ligand. The one set is with 4 ligands and second set is with 2 ligand. Octahedral complex having geometry like this. In octahedral geometry or stereochemistry, the metal atom is present at the center and surround them the 6 ligand is attached. Out of these 6 ligands, these 4 ligands basically, that is ligand 2, 3, 4 and 6 are within a one plane and form the square. And the remaining 2 ligands above the plane and below the plane, that is L1 and L6. This L1 and L6 are trans to each other. Similarly, the arrangement of metals and the ligand for the distorted octahedral complex also. But the major difference between the octahedral and distorted octahedral geometry is that in case of octahedral geometry, all the metal ligand bonds are equivalent in the length. But in case of distorted octahedral geometry, some bonds out of these 6 metal ligand bonds are shorter and some are longer with respect to each other. And that's why this geometry is called as distorted octahedral geometry. That is, all the metal ligand bonds are equivalent in the length for an octahedral complexes, and for distorted octahedral complexes, when 4 bond is shorter and 2 bond is longer, then the structure is called as tetragonal structure. Similarly, when 4 bond is longer and 2 bond is shorter, then the structure is known as trigonal structure. Basically, there is difference between the structure and the geometry. The next important point is factor affecting to the stability of metal complexes. Basically, nowadays, the number of coordinate compounds are pped, but all these compounds are stable or not. It depends on the factor which affects the stability of a complex, and that's why we have to study the factor which is responsible for the stability of a coordinate complex. There are 3 important factors which is responsible for the stability of an coordinate complex. The first factor is nature of the central metal atom or ion. Nature of metal ion or atom is very important to decide the stability of an coordinate complex. This point is subdivided into the 2 points. The first one is charge to radius ratio of a metal atom or ion, and second one is electronegativity of a metal atom or ion. The second most important factor for the stability of a metal complex is the nature of ligand. Nature of ligand is also very important to decide the stability of a metal complexes. This point is subdivided into the 2 subpoints, that is the basic character of a ligand and size and charges on the ligand. And last but not the least, the factor which is affect the stability of a metal complex is an presence or absence of chelate formation. Let us see this factor one by one. The first factor, that is nature of an central metal atom or ion, in which the first subpoint is charge to radius ratio of a metal atom or ion. Basically, charge to radius ratio of a metal atom or ion is very important to decide the stability of a metal complex. Let us see how the charge on metal atom or ion is calculated. Basically, charge density of a metal ion is calculated by using the formula charge on the metal ion divided by the radius of a same ion. When the positive charge of a metal ion goes on increasing, that time the resultant ion size goes on decreasing, that is, smaller the size of an ion. That time the metal ion is responsible for maximum attraction between the metal and ligand, and that's why the resultant complex is more stable. That means the charge on metal atom or ion goes on increasing, it results in the increasing the stability of an complexes. Let us see the example. When the complex of Fe ion with the common ligand, any ligand like as chlorine or ammonia, bromine, etc. Here keep the ligand constant. Okay. When Fe3 plus ion is combined with the ligand like NH3. Similarly, when Fe2 plus ion is combined with the ligand like NH3, that time whatever complex formed by the both ions, that is Fe3 plus ion as well as Fe2 plus ion, having different stability because this both Fe ions having different charge on itself. That's why the stability also different one. In case of Fe3 plus ion, the charge is greater than that of Fe2 plus ion. When charge is greater, then what happen? The ion will be smaller in size. When ion is smaller in size, it is responsible for the greater the attraction between the ligands and metal ion. That's why it produces the stronger bond between the ion and ligand, and therefore whatever complex is more stable than that of Fe2 plus. The second important point is electronegativity of metal atom or ion. Basically, higher the electronegativity, then it attracts the maximum electrons from the ligands toward itself, and it results in the formation of stronger bond. It results in higher the stability of an complexes. Let us see the example. Same example we consider here. The complex of an Fe ion with the common ligand. When Fe3 plus ion forms the complex with the NH3 ligand, similarly when Fe2 plus ion also forms the complex with NH3 ligand, that time the complex of Fe3 plus ion is more stable than that of the complex of Fe2 plus ion, because as the charge on metal ion goes on increasing, its electron deficiency also goes on increasing. When the electron deficiency increasing, that time it is responsible for the attraction of maximum electron density from the other sources, that means other molecules or other ligands, and it results in the formation of stronger bond. This stronger bond is responsible for the maximum stability of an complexes. This is all about the nature of central metal atom or ion, which is responsible for the stability of an complexes. And from this we are comes to the conclusion, when metal atom having more number of positive charges, then such complex is more stable than the same metal atom having lesser charges. Like Fe3 plus complex is more stable than that of Fe2 plus ion complexes. The next important factor is nature of ligand. Basically, nature of ligand is also very important for the formation of complex, because ligand having nature to donate the electron density to the electron deficient metal atom or ion. That's why the nature of a ligand is very important. As we know that the ligand having function to donate the electron, that means it having nature of basic character or Lewis base, and that's why the ligand which having maximum basic character which form the more stable complexes. Let us see one by one. Basic character of a ligand. More the basic character, more or maximum easily donation of electron density is possible, and that's why the complex become more stable. The example is carbon monoxide and cyanide anion. The second important point is size and charge on ligand. Basically, when smaller the size of ligand, then greater charge will be accumulated on the ligand. That time the maximum attraction between the ligand and metal is take place, and therefore the stability of complex is increases. That means smaller size ligand forms the more stable complexes than the larger size of an ligand. The example of such type is metal complex of metal ion with the ligand like as fluoro and chloro. Here fluorine having negative charge, similarly chlorine having also negative charge. Out of these two ligands, the fluorine ligand or fluoroligand is smaller in size because it present at the top in the group of halogen family, and chlorine is at the second position in the group. The size of chlorine ion is larger than that of fluorine, and that's why whatever electron density is spread over the larger area than that of fluorine. And that's why fluorine easily donates electron density to the metal atom during the formation of coordinate bond or DTO bonds. And that's why the complex of fluoroligand is more stable than that of the complex of chloroligand with the same metal atom or ion. The third important factor is presence or absence of chelation in the complex. Basically, polydentate ligand, that is chelating ligands, forms more stable complexes than that of monodentate ligand, because polydentate ligand forms the 5 or 6 member ring, and this ring complex is highly stable than the complex formed by the monodentate ligand, even the same donor atoms. Let us see the example. Here, for both complex ion, the metal ion is nickel 2+, and the ligand is, for first one is ethylene diamine and for second one is ammonia molecule. The common feature between these two ligands is the donor atom is nitrogen. That means both complex having maximum similarity, that is metal atom as well as donor atom. Let us see the actual structures. For tris ethylene diamine, the structure is like this: nickel atom at the center and 3 ethylene diamine molecule at the periphery. Here the formation of 6 nitrogen nickel coordinate bonds. Similarly, in the second case, formation of 6 nickel nitrogen coordinate bonds. But the stability of both complex is different. This complex, that is tris diethylene amine nickel 2+ complex, is more stable than that of hexaamine nickel 2+ complex. This is because of here formation of 3 5-member rings during the formation of complex, and here no formation of ring, and that's why this complex is less stable than that of this complex. The next important point is the difference between metal complex and metal chelates. Let us see one by one. Metal complex and metal chelate. The first difference is metal complex is formed by the monodentate ligands, but the metal chelate formed by the polydentate ligands. The second difference between the metal complex and the metal chelate is ligand in formation of metal complex called as complexing agent, and the ligand in metal chelate formation is called as chelating agent. Third difference is there is no formation of heterocyclic ring for the metal complexes, but heterocyclic ring is formed for the metal chelates. The fourth difference is metal complex is non-cyclic compounds, but the metal chelates is cyclic compounds. Fifth difference is metal complex is moderately stable, but metal chelates is highly stable. Let us see the examples. For metal complexes, tetraamine copper 2 plus, and for metal chelate, bis diethylene amine copper sulfate. The structure is like this. For metal complexes is like this, and for bis diethylene amine copper sulfate like this. This is all about the geometry, that is stereochemistry of an coordination number 1 to 12, then factor affecting to the stability of an complex and the difference between the metal complex and metal chelate. Thank you for watching.